Hello and welcome back everybody. This is Dr. Hammond for Intermediate Mechanics Physics 2500 at the University of Windsor. So in the previous lecture I discussed how to set up your second order ordinary differential equation integration routines, and in this one I'm just going to walk you through the code. So I've now uploaded the code onto Blackboard so you can work with it yourself and see what different initial conditions do to things. But I'll walk you through it myself. So I have this little preamble here that I recommend that you read. I also discussed this in the PowerPoint notes, but just what the benefits of using these second order integration routines are. So mainly we'll be using these ones. This is the Verlet and the Leapfrog methods. These are for conservative systems, so as I gave examples before, for planetary motion or for the Schrödinger equation where there are no velocity-dependent like dissipative forces. Okay, so we again import our necessary libraries. So we want to plot, so we import matplotlib. We want to have some numbers, so we need to import the numerical package for Python. We'll integrate over an integer number of steps, so about 5,000 steps, and over 5 seconds, or 5 units of time. And again, we define our dt, so our time steps, as our first step minus our 0th step. Now, because we'll be integrating twice, we need to have an empty array of our velocities as well as an empty array for our positions. So we have both x and v defined as zeros. And we have our spring constant here, but I've just incorporated the spring constant as k over m, and then I'm just going to be using our resonant frequency as this k over m. It's kind of sloppy notation, and I apologize for that, but it's just so that we can have these, the differential equation here is written just km at times x. Okay, so that is our spring constant. And so we need to define our differential equation, and so we have v dot, so the derivative of the velocity, is going to be this force over mass, or the acceleration, which is going to be negative km times x, as you would expect for a spring. So using the Verlet algorithm, we can start with some initial position. So we'll say that that's 1, and we'll start with some initial velocity of 0. And so the 0th element in our position array is going to be x naught, and our 0th element in our velocity array will be v naught. And then for Verlet, as I mentioned in the previous lecture, we need to know what the acceleration is for the very first step. But of course, we know what that is, because it's just going to be, this acceleration is just going to be what the spring constant is times this initial position. And so our initial acceleration is just negative km times x. So the first step in our Verlet position array is going to be dependent on the 0th step plus the initial velocity times dt plus 1/2 times this initial acceleration times dt squared, which is what you would expect for a constant acceleration. So this just gives us our first step. And then, as I mentioned before, the Verlet algorithm, you need to know what, for the next position in the time, like for the next time step for the position, you need to know what the current position is and the previous position as well. And so it's 2 times the current position minus 1 times the previous position plus the derivative of the velocity, so that's v dot at the current position times dt squared. And this is all we need to do to solve for the position using the Verlet algorithm, where I kind of walked through the math in the previous lecture. We can also use the leapfrog method. So again, we need to have these cleared arrays, and again, these initial conditions. Here we have both x and v as part of this algorithm. So x, the next step, I can point out that this one goes from 1 to nt minus 1, whereas this one goes from 0 to nt minus 1. So our next step in position depends on the current step of position plus the current step of velocity times dt plus 1/2 this acceleration at the current position times dt squared. And the velocity at the next position depends on the velocity of the current position, and then 1/2, and it's the average of the two velocities of the current position and the next position times dt. Both of these give about the same error, and I think it's dt cubed. And so we can put that as this position array x underscore LF, so for leapfrog. And then the exact solution, we know what that is because we're starting off with initial position of 1 and initial velocity of 0, so we know this solution is just going to be 1 times cosine the square root of k over m times t. And we can also compare this to built-in solvers. So if we have, so you can use this SciPy or SciPy library and import this ODE int solver. So we define our function, and now because this is a second order differential equation, we define this function of y, but y is actually composed of x and v. So v is all of our functions that we want to integrate, or that we want to have the answers for, and we want to integrate over t. And so we need the derivatives of x, which is v, and the derivative of v, which is minus km times x. And that's all we need to do, and we return these derivatives. So it's really simple. Again, we just need to have two functions to call, or two things that we need to call in this function. But y contains two arrays that we want to be integrating over, or variables we want to be integrating over. And then we have to put in our initial conditions. So y0 or y0, it's going to be x0 and v0. So we have to keep these in the right order because we have x and v here, and so the derivative of x and the derivative of v. So we just need to keep everything in order. That's kind of the only thing you need to pay attention to. And then to solve for this ordinary differential equation, we just call ODE int, and we put in the function here, our initial conditions and this time, just like we've done before. And our position from this built-in solver will be the 0th row of this p-soln array or matrix. Of course, we'll have two values, two elements of how do I want to say this? We have, two rows of these columns that are nt long. So the 0th one will be x and the first one will be v. But in this case, we don't care about v because there's no velocity dependence. And so we run this, and we get these oscillating functions, and we can see that these all agree quite well. So I have the exact is black and leapfrog is blue, and they all agree very well. And we can look all the way to the end, and these things all agree quite well. Whereas they start to separate just a little bit between the leapfrog and Verlet agree quite well with each other, but there's a little bit of separation between the built-in solver and the exact answer. And so we can, if we want to check how quickly these things diverge depending on the number of time steps we have, we can see that if we don't have enough time steps, that we start to get the leapfrog and the Verlet, although they keep the amplitude quite well, which is what we're expecting from these symplectic algorithms. They keep the amplitude, or they keep the amount of energy in the system, which is nice. You can see that the phase starts to change. So they start to become a little bit out of phase, or the position's slightly wrong compared to the exact or the ODE and built-in solver. And when we get to the end, these things are basically out of phase. So the built-in solver is green, the exact answer is black, and you can see that those agree extremely well. And so this built-in solver doesn't require very many time steps to be able to solve this very accurately, whereas Verlet and Leapfrog aren't quite as accurate. So you'd want something with a slightly smaller error growing as a function of dt. So something that better than dt cubed. So I guess you want something dt to the 4th or to the 5th power. All right, so that's it for talking about conservative systems. And in the next tutorial or lecture, I'll talk about when we have non-conservative systems.